How is what? No, we got used to it. It's actually very nice. It's a little bit small, but we got used to it. Yeah. Right. It's okay.
We still got technical problems here, JP.
No problem. I'm not in a rush.
It's very clean. It has everything that we need in it. We also have a coffee machine and a kitchen and so on. So yeah, no, it's actually very nice. It was a little bit a shock because it was not what we expected from the pictures. The pictures were deceiving. But having slept there, slept well, things are good.
Yes. Okay, yeah.
The break is so. Yeah, send me a brief message. What happens? Yeah.
JP, can you say something, please?
Yes, sir, I am here. I'm waiting for you. Any sound yet from me?
Yeah, we can hear him. We've got to turn off the feedback.
Testing. Testing, 1, 2, 3. I don't hear any sound on your side now.
How about now? Can you hear us now?
Yes.
Okay,
Yeah.
good. All right. If you could all take your seat, please. We finally got the fine tuning. The point. Okay, so we're very delighted to have with us this afternoon JP Paglione, Johnpierre Paglione. JP was planning to be here in person, but personal events meant that he had to cancel at the last minute. So we're delighted that he can still join us by Zoom. JP and his group have been working on uranium ditelluride for the last few years since they discovered it. When was that? Back in 2020?
No, late 2017, actually.
2017, okay, and it's proven a lasting and fascinating enigma, and he's going to tell us about their latest results. So the plan is, well, if you can hear us, we'll interrupt you for questions.
Yes,
and the
no
plan
problem.
is 50 minutes plus half an hour, but we'll probably absorb about 20 minutes of that half an hour during your talk. But if you can definitely wind up 10 minutes before the end of the 1 hour, 20 minutes, then we can have a decent question period. So take it away, JP.
Okay, thank you very much. And yes, please do interrupt me with questions as you have them. And we'll try our best to do this through Zoom. Piers reminded me that this was actually the second time that I somehow ducked out of attending in person. So I apologize for that. Yeah, just unforeseen circumstances prevented me from coming this time. So hopefully I'll catch up with some of you at another time, or please contact me if you have further questions. The other thing I wanted to mention was that, as Piers mentioned to me, there wasn't much, let's say, overview of UTe2 in the previous, in today or previous talks. So I will do my usual task of sort of going through some of the recent events and updates as best as I can, at least as it relates to what I'm going to talk about. And we'll see how that goes. So please ask me questions and I'll try to answer as best as I can. My plan is to, as I said, kind of go through what are sort of some of the recent events and updates, nice results coming from various groups. And at the end, I'll talk a little bit more specifically about some of our thermal conductivity measurements, as well as some new ultrasound data that we're working on with a group of Brad Ramshaw at Cornell. So hopefully we'll get to that and we'll get through some interesting data. Okay, so you can see my mouse, is that correct?
Yep. Yes,
Okay.
we can.
Yeah, sorry, I can't use the laser pointer, somehow it slows down my screen. So just to acknowledge many collaborations that we've developed over the years on this, on this project. We've been working on it for several years now, amazingly, and it's still vibrant and very interesting, so that's good. And I think we're getting somewhere. I think we're getting towards some understanding of at least some of the phases in this material. And they're quite exotic, I believe. Just to point out, of course, our close collaboration with the group of Nick Butch, and it was actually Sheng, who was Nick's postdoc at the time, that discovered the superconductivity in the labs in our facility in Maryland. So that's the kind of basic story. And then we've worked with many people over the years on STM, microwave, Kerr effect, theory, et cetera, more recently, nice STM work coming out of the group of Seamus, and still working with video on that. And as I mentioned, the ultrasound data. And we've been working with Peter Hirschfeld on the theory of the thermal conductivity quite closely. And I just had to email him now saying I'm running late and we're supposed to meet right after I give a talk on Zoom to discuss some of the new data. So I don't think he's listening. Okay, so let's start from the basics. This is actually the first data set of resistivity that Sheng measured back in, I think it was late 2017, of the resistivity. And he came and showed it to me in the hallway, and I said, oh, that's kind of cool. I think, you know, maybe there's something there. TC is a little low, but I had no idea that this was going to lead to such amazing, interesting data and investigations and so on. So we're very happy that we were part of that excitement, and continues to be moving along in both our groups, Nick and mine. And you know, over the years I've shown sort of a slide of some snapshots of recent highlights and interesting papers, and this is one of the older ones, of course. And I've been adding it over the years, and you know, this was a few years ago. There was some hype about more interesting results about high field and so on that came out of various groups, including interesting graphics, as you can see here, that I don't know what they mean, but you know, they catch people's eye, so that's good. And then, of course, it's just evolving continually. So you know, this was new results as of the last March meeting, 2024. Which came out from the Cambridge groups, the high field work that was just mentioned in the previous talk, and then work from Nick's group and mine on the high field phase, function of angle, and so on. And then in our own group, working on trying to do some tunneling work and point contact work, and that's also evolving. And then, you know, I had to add this slide just to update things even further, because there was a whole slew of STM data that came out in the last, I don't know, 4 months or so. It's quite amazing. And, you know, we went from beautiful work by Vidya in the first part of our results, showing some signatures of chirality at step edges on the superconducting state, in the superconducting state. And that's evolved to some observations of charge order, at least on the surface, or, you know, it's still being investigated. And then work by Seamus using an STM tip, which I'll talk a little bit about, investigating the order parameter as well. And then the most recent data showed beautiful work on the vortex lattice by several groups. I won't go into details on these, but just to flash them, and you can, I think they're all on archive still, not published yet. But some amazing stuff, for instance, the double vortex structures that have been seen recently, as well as some, you know, I guess there's some controversy between whether there's some time reversal braking effect, as shown in this work, versus no time reversal braking effect, in the sense of flipping the magnetic field and looking for signatures of time reversal braking in the vortex cores, or the vortex structure at least. So some really exciting data to follow up on and see where this takes us as we go along. Okay, so as some of you may know, the some of the really amazing work has come out of the yield of the crystal growers, and the extent that you can grow crystals of varying quality, and in particular different TC from 0 up to upwards of 2 Kelvin, using slightly different growth parameters. And I just want to emphasize that, you know, the changes in crystal growth are very subtle. It's not like, you know, we're turning a switch on and off. We're just subtly changing, for instance, the temperature of the furnace, and you can get different crystal growth. So it's not a matter necessarily of different impurity content, but it's probably something more to do with a level of disorder or vacancies. It's changing as you turn that knob on the furnace. And that gives a really nice control knob on studying the evolution of the superconductivity, at least, which seems to be the biggest benefactor from that knob, in the sense that the normal state doesn't, at least as far as I can tell, doesn't seem to change as much as the superconducting state, at least in terms of the strength of the pairing. So that's an interesting knob, and we've been using that over the last few years to study things. And so this was first, you know, reported by the Haga group, where they made a breakthrough by growing crystals using a novel salt flux technique, literally table salt, molten table salt, to grow crystals. And that gave the ability to grow the highest TC crystals to date, about 2.1 or so Kelvin. You can get close to that with the original vapor transport method. And in fact, we reported recently that you can use a tellurium flux method to grow high TC crystals, and that's in our thermal conductivity studies. So I'll get back to that. The good and bad aspect is just that UTe2 has a sort of large width of formation. And this was reported way back in some of the first papers on this compound, in the sense that they reported that you can grow UTe2 when you turn the knob of the furnace by a few hundred degrees. And now we know that as you do that, probably some level of vacancies changes to give you a higher TC, surprisingly on the lower end of temperature versus the higher end. So it's kind of counterintuitive to us, you know, materials growers, in the sense that typically you want to grow the best crystals in the highest temperature, richest flux environment, you know, lots of tellurium around, for instance. But that's the opposite of what happens here. Okay. So that's the story of the growth, and that's, you know, people are still working on this, but that's seems to be the state of the art now, that you can grow crystals with very, very low residual resistivities. There's still some questions about what the relation is between TC and the residual resistivity. I don't think that's mapped out quite well. And at least some of the work by Nick's group here has shown that there isn't a clear correlation between resistivity and TC. There is some spurious points that go all over the place. So it's a bit hard to map out, especially due to the anisotropy of the transport, but we're working on it. Okay, there's also some recent developments. Well, it's been evolving as well. The understanding of this band structure, and interestingly, Piers just mentioned before I started the talk that there's some, you know, just ongoing discussion about thinking about how the F electrons fold into this band structure. Some of the original work was really just showing that, you know, first of all, when you just do a plain vanilla DFT calculation, you actually get an insulating state. And as you have to crank up U a little bit to get a Fermi surface. Was there a question? No. Okay. So some of the earlier ARPES work done very nicely by Andrew Ray's group, show that this Fermi surface of sort of cylindrical like pieces that comes about from these 1D quasi 1D sheets that derive from the uranium tellurium chains, actually is borne out in experiment and observed very nicely. And, you know, they have some factor of 10 or so different dispersion. The tellurium sheets are a little bit faster than the uranium, but these are P and D components of the Fermi surface. And there's still some ongoing discussion about where the F states are to some degree. Originally, there was some observation of an F-weighted, more 3D pocket, and that's I know been a controversy in the community. Amazingly, with the advent of these lower resistivity crystals, the first quantum oscillations were observed a few years ago now by Aoki's group and Haga's crystals, and they showed very nicely that the proposed Fermi surface actually is pretty well observed in quantum oscillations as well. So this quasi 2D sheet Fermi surface works pretty well with the fact that the effective masses are very heavy. So that was really nice to see and confirmed. And of course, there's been lots of studies since then. Sheng's group, for instance, reported some similar results, but also claimed observation of some small pocket that has been argued against in terms of whether it's a actual Fermi surface or it's a sort of breakdown orbit. And the Cambridge group has been working on this as well, to show that perhaps this is a very novel study, just to say that using this proposed breakdown orbit to actually do some fermiology is what they were claiming in their work, to show that there is no 3D pocket, and that you can explain all of the band structure, or at least the Fermi surface, I should say, with some warped cylindrical shapes. So, I wouldn't say this is completely fleshed out, but there's lots of work now to suggest that this is a mostly 2D Fermi surface. That's all I'll say there. Okay, another interesting update follows some work that we did several years ago on trying to carefully measure the anisotropy of the transport to say something about this band structure. And so this was my postdoc at the time, Yun Suk, who's now at Texas Tech. He did a very, very careful study of preparing crystals in various shapes and orientations to carefully measure the anisotropy. So of course you can get a big crystal of UTe2 and cut it in the right direction for C-axis, but the fact that there's some anisotropy can always give you some error if you don't do this carefully. And so we wanted to be sure, and he actually did a very nice study, and he actually developed a sort of analysis technique, which he called, I think it was like the modified Montgomery technique, to try to analyze data that he took that was of a non-square geometry. And so just to say that this data was confirmed quite nicely in various samples and so on, and we were quite confident that the anisotropy was actually this. So A-axis resistivity was the lowest, and surprisingly B and C were near each other, so about a factor of 2 larger than A. And then on top of that, the fact that there was a quite different temperature dependence to the C-axis resistivity with this peak structure around 15 Kelvin rather than this broad drop around 50 Kelvin, which is usually associated with the Kondo coherence development. So that was a surprise, and it seemed to fit at least to some degree with this picture of quasi 2D Fermi surface plus some 3D pocket, sort of a 2-band or 2-component conductivity model. And so we were surprised when we saw some recent work by Philip Moll's group, where they did a beautiful job of fibbing out a crystal to be able to measure directly the anisotropy. And surprisingly, they showed that the resistivity, you can see in the top right here, for C-axis is actually about 50 times larger than the A and B plane transport. So, and actually, not only that, but they also claim that the, sorry, I can't see my own screen because of this. Oh, shoot, I do something here. Okay. The Zoom thing is in the way. Okay, so there it is. So surprisingly, they show that the A-axis resistivity shown in red here is actually higher than B. That's flipped from what we previously observed. So, this is new data. I don't know. I'm not saying I don't believe it. I think it needs to be remeasured and checked very carefully. I tend not to believe that the C-axis is that much higher. But for example, we measured Wiedemann-Franz law and the C-axis resistivity in our previous measurement. So it's a bit hard for me to believe that it's that much different than the other crystals. But perhaps it is, and that's a new piece of the puzzle. Okay. Okay, so NMR is another interesting evolution of the story, and I won't go into details. There's been at least a dozen papers on NMR, starting from our original claim of lack of night shift change through TC, which was one of the original pieces of evidence of this being a triplet paired state at ambient pressure and low field and so on. The Aoki group and collaborators have studied this through various studies, different crystals and so on, higher quality over the years, and basically come up to this story where there's a small night shift drop they observe in all three directions of the field. And they claim that this is consistent. Well, this at this stage, at least, they claim this is more consistent with an AU symmetry for a P wave state. The most recent paper is this one, which just appeared, I believe. And they did a nice job of basically an analysis where you take the tellurium NMR signals from the two tellurium sites, and you do I don't quite understand this, to be honest, but you do a subtraction of the two. So here's the two tellurium signals, for instance. You do a subtraction of the two, and that should give you the intrinsic superconducting response. And they claim that, here it is. Here's the data they published, and there's some very slight change still at TC. So, okay, I don't know what to say about this, but at least there's a small change, and they say that's consistent with the D vector that may have components in all three directions. So that leads to the question, what is the order parameter structure, even at ambient pressure? And of course, in the other superconducting phases, there's 3, 4, maybe 5 different superconducting phases that have been reported as a function of pressure, magnetic field, and both. And so, how do we map this out? And that's still an active area of research. I'll go back to another one of the original results, which is still also anomalous, and that's the penetration depth measurements. So there's two main results I'm aware of. One is from my colleague Steve Onlaga at Maryland. This was in our original thermal conductivity paper, where they just saw a nice quadratic temperature dependence of the penetration depth that was reported. And then more recently by the Shibayuchi group, where they actually studied different quality crystals, lower and higher TC, which you can see here. And they also saw quadratic. And in this experiment, they oriented the magnetic field, which is their coil in their measurement, in different orientations. And they showed that it's pretty much quadratic in all three directions. And so if, in a traditional superconductor, if you see quadratic in all directions, it essentially means that you have some kind of nodal excitation oriented in at least some component of it oriented in all three directions. And that led them to propose some multi-component order parameter, because a single component order parameter would only have nodes along some principal axis and not the others, for example. And there's some follow-up work by the Onlaga group where they studied this even more carefully, even in the higher TC crystals, and it's still the same story. They see quadratic response. And more importantly, they also see an abundance of low energy excitations, which kind of, raises more questions than answers in some sense. So one possible way out of this came out of a very beautiful theoretical work by Brian Anderson, which was presented at the March meeting this year. Basically, I'm not going to go into this in detail, but they show that in addition to the symmetry imposed nodes, which are, depending on the order parameter you choose, B2U, B3U are kind of the favorites. There's additional point nodes that, in his words, are hard to get rid of. He says that they're there, and they take on positions that are not along the high symmetry direction. So if that's true, then that may lead to an explanation for some of these anomalous results in at least in penetration depth and perhaps in NMR as well. I'm not quite sure. And of course, other studies that I'll also flash in terms of STM work. So this is quite interesting, and this is, I should just say, this has brought us far beyond the sort of simple, at least what I learned when I was younger, simple point node P wave kind of structure that you think of when someone says you have a P wave superconductor. So it makes it a little bit difficult to try to really nail down what the order parameter is, but it makes it fun too. Okay, so again, the question to some degree still remains, what is the order parameter? Originally, we proposed that it was a multi-component order parameter, and that was based on observations of a non-zero Kerr effect below TC as measured by the Capitolnik group, as well as our observations of actually two superconducting transitions, and that was the original observations in the first generation of crystals that we measured a lot of. And since then, of course, that story has evolved, and the higher TC samples do not seem to show double transition, and at least one other Kerr effect experiment from the Los Alamos group also tends not to show Kerr effect. At least a spontaneous Kerr effect below TC. So, okay, it is what it is. And of course, when we're in doubt, we have to go back to the lab and do more measurements to understand. So I'm hoping at least, these groups will pick up more measurements and look at more crystals and so on and try to understand when they do and do not see Kerr effect. And we're still interested in understanding when we do and do not see multiple TCs and so on. At ambient pressure, at least. Okay. So in our collaboration with Seamus, their group did some beautiful work using a niobium tip STM setup, and using the niobium tip allowed them to actually extract the nature of the spectroscopic gap, across the sample surface very nicely. Because with a normal tip, it's actually very difficult because there's a lot of in-gap states at the surface, and that's not exactly clear why, but there's certainly low energy excitations. And now we believe that that's due to existence of surface and Dreg bound states. And so this was a nice study which was verified by a model by Donghai Lee, okay, so first of all, doing this experiment shows, I didn't show the data here, but it shows a zero bias, very large zero bias response in the superconducting gap of UTe2. And so to try to understand that, Seamus's group did some very careful studies to raise and lower the tip towards the surface and show actually that as you lowered as you increase the conductance, so as you lowered the tip towards the surface, you actually saw a splitting of this zero bias peak right here. And so to model that, Donghai proposed, well, if this is a chiral or non-chiral order parameter, you will qualitatively see different responses on the surface based on whether you have topological states that are spanning the gap or not, and whether they can be split, for instance. And so this seems to be consistent with the non-chiral single component order parameter picture, in particular B3U, and I'll show another slide where that seems to be pointed to by the STM work. Anyways, I really like this result, first of all, because this beautiful splitting that you can turn on just by changing the tip distance is quite provocative. And it seems to give at least some answer to this multi-component versus single component order parameter. Now, B3U implies that the nodes are along the A direction, and so this is a very subtle thing. Whether it's A direction or B direction of nodes, B2U would imply B direction, and we have some results that may not be consistent with that. We're still working, and I'll get to that. Okay. Any questions so far?
No questions.
Okay, I guess I'm doing a good job. Okay, so also to answer this question of multi-component versus single component, we teamed up with Brad's group at Cornell to measure ultrasound. And as many of you probably know, ultrasound is a very powerful probe of the symmetry of an order parameter at a superconducting transition. And that's because it probes the sort of distortion of the Fermi surface as you strain the system with shear and compressive modes. And at least in a simple picture, you can distinguish between a single component and multi-component order parameter. Here, the example shown px plus ipy from a very famous material I won't mention. There's a very sort of smoking gun kind of result that you expect in this case, which is if you measure the shear elastic constants through TC, yeah, if you have a multi-component order parameter because of this distortion, you would expect a jump in the shear moduli, as opposed to no jump or just a kink if you didn't see that. So Brad's group measured this a couple of years back, both using resonant ultrasound and pulse echo, and importantly, they were able to do a measurement on both samples that had a single superconducting transition as well as samples that had a double superconducting transition, which you can see in the solid red here. And the important result is basically that when they looked at the shear elastic constants shown in purple here, there was no sign of a jump. It was just kinks, and C44 actually shows a very anomalous lack of anything. But no jumps, at least the resolution that was measured. So that puts a constraint on possibility of being multi-component and seems to point towards a single component.
How do you understand this? I mean, this seems to be done in a low TC sample. So, I mean, how does that reconcile with your heat capacity?
I'm sorry, can you repeat? How can you what?
I mean, you said in the lower TC sample, your heat capacity showed two peaks, right? Two components, and the higher TC sample does not. So
Yeah.
I mean, this seems to be done in the lower TC sample, right?
Right.
So how does that reconcile with your heat capacity data?
Yeah, so we actually measured for instance, this sample S3, we measured the heat capacity of this sample, and it did show, a sort of shoulder in the TC. So there was two TCs in that sample. And whereas in S1, you can see very clearly it's a sharp single TC. So, you can grow crystals that have a lower TC with vapor transport that don't show a double transition. So it is what it is.
So in the sample sample, I mean, has he done the measurement in the salt growth sample on this?
In the salt flux sample, we are doing that now. Yeah. Yeah. I'll get to a comparison of these different samples, at least in the eyes of thermal conductivity. But this is the work so far on the ultrasound data. We also have ultrasound data under pressure, which I'll get to. So at least in the picture of looking at the compressive constants, this was Brad's idea that if you think about the sort of magnitude of the jumps along the different compressive directions, A, B, and C, it was interesting that C22 showed a very weak feature at TC. And so the idea was that maybe that's consistent with a B2U order parameter in the sense that the superconductivity is weakest if it's along the nodal direction, and strongest if it's along the anti-nodal direction. And so that was just I would say a secondary suggestion that that this data is more consistent with a B2U order parameter. But as I said, there's some interesting results in theory and experiment that suggest that it's not that simple. So that's still a challenge to try to understand that. And there's more to the ultrasound, which I'll get to in a second. Okay, so now I'm going to switch to the thermal conductivity, and this was our original work back in 2019, where we we studied the first generation of superconducting samples to try to understand if there was evidence of nodes, evidence of low energy excitations, and so on. And so we actually studied two samples with heat currents applied along the A and B directions. And to make a long story short, we saw a zero intercept of the linear component, but a rapid rise with temperature and a rapid rise with magnetic field at the sort of zero temperature limit. And these data are consistent with there being some kind of nodal excitations. So we concluded that there's a 8-point node symmetry. We just couldn't quite nail down what the symmetry would be at that time, at least not without directional dependent studies. And that's what we've been doing, and that's what we're doing now, actually. So to our surprise, the Matsuda group reported in the higher quality, higher TC samples, something which appears quite different, at least to the first glance. And that's a very more activated like behavior, for instance, in the magnetic field evolution, showing what looks like zero activation as you increase the magnetic field. Shown here, for instance, in this zoom of the temperature dependence, where this data all points towards zero, and there's no behavior with low magnetic fields. So we were actually doing the same study at the same time, and we knew this data wasn't consistent with our own. So I'll show a little bit more data about what our opinion of this result, which is essentially just a story of doing measurements to lower temperature and doing extrapolations properly. Okay, so I'll also remind just, and this was studied by various people, including Ilya Vector back in very late 90s. The thermal conductivity is a function of magnetic field in nodal superconductors is a kind of rich field. Just to say that when you have nodes, of course, they're going to be sensitive to disorder, and if you're measuring the excitations of those nodes, you should be careful about what that effect is. So what's unusual is that in most nodal superconductors, we are not quite at this level of sort of extremely high purity. And when you get in this high level, it was actually reported in a simple model back then that the thermal conductivity as a function of magnetic field does actually, or I should say, does not show any increase, as you would expect, for instance, from the so-called Volvic effect at very low fields. And it's quite flat. And so this was actually measured in potassium iron 2 arsenic 2 by Louis Taillefer and company, which is a very high purity, most people think of unconventional superconductor. And you can see that there's a very slow rise in thermal conductivity. We actually did the same measurements here, and this is our data. We didn't publish the same thing. Now there is a intercept here, which you can then very clearly point to and say, well, this is obviously an unconventional superconductor because it has T linear excitations at zero magnetic field. In UTe2, we don't have that actually. So it's a bit more challenging to convince yourself that it's not just a fully gapped superconductor. So here's the data that we recently published actually. So now these are the samples that we grew actually with a self-flux technique, but you can see that the triple R's are as high as you can get. And the residual resistivities are below 1 micron centimeter. TC is about 2.1 Kelvin or so. And so we get very nice data from these crystals. And we did a thermal conductivity study, not of just this sample, but of a sort of series of crystals with varying TC and varying quality, just to see what is the evolution of this story. And here it is. So basically, if you just look at the temperature dependence at zero magnetic field for samples with varying TC, which means varying quality. And you can see, for instance, right away that the little kink here is the TC. And you can see that the rapid rise below TC is an enhancement of conductivity. And that's due to essentially a loss of scattering. And you can see that increases quite dramatically when you get to the highest TC crystal. You see this very large rise. So that's a sort of intrinsic measure of the impurity, or I should see whatever is causing scattering in the crystal. So the scattering is much less in these highest quality crystals. But you can see that at the low temperatures, these data all point to 0. So there's no linear term and so on. It's still 0, but that's consistent still with a clean limit point node superconductor. In particular, the fact that you have a rapid rise of temperature is very hard to explain with a fully gapped situation. So that's sort of, conclusion number 0. But of course, we can measure the intercept as a function of magnetic field, and you can see that's what's done in these 3 panels for the different sample qualities. And you can see in each case, there's a fairly rapid rise, which changes, and you can quantify that by actually mapping out the field dependence. So here's where you have to, okay, for instance, if I look at the highest quality sample here, you got to look at the scale of temperatures here that we're measuring. This is below 50 millikelvin, and you can see there's still a strong curvature of the data, even at that temperature. So you have to be very careful about how you're extrapolating these things. If I were to extrapolate from above 100 Kelvin, I could get various things. In fact, I would get a negative number if I did a linear extrapolation. So the key here is that we measure to the lowest temperatures possible, and then we're able to look at the magnetic field dependence. So we use extrapolated values, but you can see that that's pretty, even if you just took data at 50 millikelvin, it was sort of the same thing. So the key result is that when you apply a magnetic field, it does rise rapidly. It's just that the scale is much smaller. And you can see here, for instance, if I normalize the thermal conductivity to HC2, that's what's shown here. The lowest TC samples show a rapid rise towards HC2, whereas the highest quality crystal, S3, for instance, shows what looks like a no rise at all, but you zoom in here, and that's what this data is here. And you can see that there indeed is a very rapid rise. This is Volvic effect, but it's just scaled by the scattering rate. Well, I'm sorry, it's scaled by HC2. So if I scale it by HC2, then I don't see any change, which is nice. That's actually a conclusive confirmation of it actually being Volvic effect. If I plot it as absolute magnetic field, you can see that the highest TC sample rises rapidly first. Okay. There is, of course, okay. Sorry, I got a step here. So what I'll say about the Matsuda data and the result there is just that we basically have measured to lower temperatures. So the limit of their claims is from extrapolations above about 150 millikelvin. And so, as I said, you have to go to lower temperatures to really see what's happening here. And it's quite novel that we were able to do this and show this very rapid rise. So it's this data way down in this little corner that's important. One more thing about this data, as you might have noticed, there's a sort of maximum around half a Tesla, I'm sorry. And we don't quite understand what that is yet, whether it's a, something to do with vortices, or something else happening in this basically 0 temperature limit. This is not very well studied because of various complications of doing thermodynamic measurements below a few hundred milli-K. So we're still studying this, but I will say that at least the very low field rise seems to be consistent with the Volvic effect. So we're pretty confident that this is a point node superconductor, whether the TC is 1.6K or 2.0. Okay. Yeah. So okay, so I have how much time do I have left? Maybe 20 minutes, 10 minutes?
Yes, 20 minutes.
Okay. Any questions at this point, I should say? No. Okay. Okay, so the next step for us.
We are paying attention. There's a lot of material. We appreciate it.
Okay, that's why I'm asking.
Yeah, no, it's, I was just talking about, an infinitely more simple material this morning, and it was already too much information. So, So.
Yes.
You're doing great, and you reminded me of, new materials, how there's so many pieces to put together, and how you have to, to keep track of all the pieces. I think it's really impressive.
Yeah, and this part is really just focusing on the ambient pressure, low field superconducting state, which is already, we've been studying this for 6 years. So understanding that state, of course, is a launching pad for the other states. And so just to, I gave a sort of overview, but I'm now focusing on that state and trying to understand what is the order parameter there. And it's not easy. It's not easy to answer. And then the last part, I'm going to talk about the pressure phase diagram, which is more complicated as well. So please interrupt me if you're confused or have questions about any of this. I don't have to finish this.
Can I ask a question?
Yes.
Yeah. So when you've been normalizing your plots of the thermal conductivity, you've been doing it with respect to HT2. You've been plotting against H over HT2, I think.
Both ways, actually. So if I
just
if
wondered how you're defining HT2, because we know that the superconducting state changes with field. With what definition are we using there?
well, we so let me see. In the so in the lower TC samples, so this, by the way, this is all for A-axis magnetic field. So in the lower TC samples, we can actually get to the normal state easily. And so we see Wiedemann-Franz law, for instance. So that's an easy confirmation of being in the normal state. So we use a definition of where the resistance becomes normal, and then confirm it with thermal conductivity. In the higher TC samples, we try to do the same thing, but we may not be able to measure it because of the higher field. So basically, the HC2 definition is the resistive HC2.
So all these measurements are field along A direction.
Yeah, that's right. And so actually, you remind me to point out one more thing, which is kind of interesting. So if you normalize to HC2, which is kind of the standard way of doing this, as I said, you see a quite different behavior, right? But if you zoom in at very low fields, then actually it's uniform. It's kind of universal slope, which is what you expect for Wolowik effect. It's scaled by HC2. If I go back to the unnormalized data, just this third panel here, and I look at higher fields, we pointed out in this paper that the increase is actually pretty much parallel for the different samples. So we actually think we're in a different regime here, where the increase in conductivity is not dictated by the scattering rate of the sample, but by something else. We're not quite sure what that is yet. This is a more complicated regime because of vortices and so on, but there is something interesting here in the fact that these all rise at the same rate. Okay.
GB, since you're
Yes.
on this slide, this is Andre. Could you say, could you contrast this with Matsuda's data? I don't know if you want to, but could you say what they measure, at least what the claim is? You showed briefly before.
Yeah. So the claim is that they measured in the low field, low temperature limit thermal conductivity, and they say that there's no increase in the T linear term with low fields, which is consistent with a fully gapped superconductor like niobium. So they claim that the data they measure is in the light blue here, and that this is just zero. It's essentially activated until you get to a fairly large component of HC2. And what I'm saying is, no, they're basically their error bars are too big to say that. And if you zoom in here, in other words, if you measure to lower temperatures, notice this temperature is 120 millikelvin or so. So if you measure down here, then you see this. And so you do see a rapid rise, and you see this very rapid rise at low fields. So I'm saying that their error bar is sort of this whole range, and we're able to discern. Does that make sense?
Yep, thanks.
Okay.
Can I ask then, also James next, is there a power law there at the low temperature? It doesn't really look like T squared. It's obviously not linear, it bends over.
Right.
Fit there, is there a particular power law to that fit?
Yeah, it's some power law. I forget what it is. It's maybe 1.5 or something. You know, this really depends on the model you use, you know, so there's no strict power law unless you have a very simple P-wave superconductor. But it's we try to use the same, so what one thing we enforce is that we just use the same power law at least to try to model the data extrapolations. So some different coefficient. If you start changing power laws, well, you know, you need some understanding of that. I think that was another issue with the Matsuda analysis. They actually changed the power law as they increased the field. Okay. So the next step was to try to locate where the nodes are. And this, so we teamed up with Peter Hirschfeld and postdoc Vivek Mishra, who's basically doing all these calculations. And this is going back to an old idea, which is essentially rotating the magnetic field with respect to the nodal positions. And because of the Baldwin effect, you can sort of vary the amount of excitation based on the Lorentz force of the excitations with respect to the field direction. So for certain orientations of magnetic field, you will, in essence, have excitations from all the nodes. And if you tilt the magnetic field direction, you'll have more, I should say, you'll have less excitations from certain nodes that are aligned with that direction of field. So in essence, if you rotate the magnetic field, you should have the least amount of, here it's density of states, but the amounts to the conductivity when your field is along the node, kind of like this picture here, as opposed to with the node, perpendicular to the node. Okay, so that was a prediction from a long time ago, and another novel prediction was actually that when you change the temperature of this effect, there's a crossover actually where you actually go from a minimum of conductivity along the nodes towards a maximum. And that's a sort of trade-off of the thermal excitations versus the nodal excitations due to the Volvic effect. So we went about trying to do this, and both theoretically and experimentally. And what I'll say is the data which I'll show you is very simple in the sense of it seems to match this picture really well. But then when we start to look at details of the calculation in terms of using a real Fermi surface and so on, it gets complicated again. So we're actually right in the midst of trying to understand what order parameter best fits this data. Okay, so at least in a simple kind of picture where you have a single component order parameter, and we're comparing always B2U versus B3U, which means nodes along the B axis versus nodes along the A axis. And you can see, for instance, let's see, this is B2U, I'm sorry. If you this is a simulation now. If you look at thermal conductivity, there's a minimum along when the field is along the B axis, as opposed to the other case